A very good afternoon to all of you, my dear participants. First of all, congratulate each and every Indian who are residing in India and abroad for successful launch of Chandrayaan 3. Come to our topic of this course. So today's our topic of lecture is crop water use, water stress, irrigation water requirement studies using earth observation and geospatial technology. Although the topic has a wide coverage in terms of its application part, so I try to cover few basic things with follow up of case studies so that you may get a better idea, quality information about the particular theme and use of geospatial technology in particular application. So today's our topic of discussion in terms of content part, I will discuss in this particular lecture the crop water use or the crop yield transmission, the definition and its basic processing part. Then crop coefficient approach, which is used very much widely at global scale for field scale as well as for using remote sensing data sets based crop yield transmission estimation. Then reference yield transmission, what is the basic equation phenomena, what are the parameters which are incorporated here. Then remote sensing based crop coefficient method, follow with a case study. Then I will discuss about the surface energy balance, which is remote sensing based, and where I will discuss about the one source and two source energy balance model from scatter plot to physics based model with a follow up of case study. Then in recent advancement, people are using, researchers are using UAV, and currently various agencies are also working in the domain of UAV, unmanned aerial vehicle, for crop mapping as well as the crop condition with follow up of crop over transmission assessment, and which is a very precise and quality technique in the same application. So that same case study I will discuss in this lecture also. And water stress assessment using remote sensing, irrigation water requirement using remote sensing, follow with a global and regional ET products which are free in terms of nature and where you can easily access the data sets at global scale. You can and check it out for your region, for your local location, and you can easily download free of course those data sets. So I will start my lecture with the topic of very first crop water use, the need aspect. So what is the requirement of this particular topic? If I'm saying what is the crop water use or crop water requirement, it is a total amount of water which is needed as a process of evapotranspiration. And that evapotranspiration from sowing to harvesting, or you can say the planting to harvesting for a particular crop, a particular climate or location, and that ultimately not limit the plant growth and crop yield, so that plant growth may not hamper. So the amount of crop water use and crop water requirement define the particular quantity. So only out of the water which is taken by the plant uh, via its root, which is around only 1% is used for its photosynthesis and metabolic activity. Rest of around 99% of water content is simply evapotranspire for its metabolic activities as well as for cooling down of its surface from extreme heat condition. So the crop water requirement or crop water use, it's ultimately used for precise estimation or calculation of irrigation water requirement, irrigation scheduling, water budgeting and water allocation for a canal network area, for a basin level or catchment level. So we can easily access how much water we have, and according to we can manage our water in terms of better distribution for irrigation purpose for a potential agriculture production. So come to the definition part. What is the crop evapotranspiration? So in standard condition, as we denoted with ETC, a evapotranspiration is a combination of water loss in form of evaporation from soil and transpiration process by plant. So it's a combination of evaporation and transpiration from a disease-free field, a well-fertilized crop, a larger area, or you can say a homogeneous patch with a optimum soil moisture condition, all full, as well as it's achieving full production. So it terms of like all the conditions are well addressed and good in terms of crop production. It is that at a time the water loss rate defined as crop evapotranspiration. So the right side of this particular slide clearly show the partitioning of evapotranspiration in form of evaporation and transpiration from soil as well as the crop respectively. So from sowing to harvesting, as the LI is increasing, the transpiration fraction is increasing, and subsequently evapotranspiration fraction is decreased and become minimum at the time of peak vegetative stage. But after the transformation from vegetative phase to reproductive phase, follow with maturity and senescence, the slightly soil evaporation may increase because of the senescence or the leaf shedding of the lower leaves from the crop plants. Come to the part of various approaches. So very first, the crop coefficient approach is most widely used at the global scale, not only for the field scale as well as using remote sensing or geospatial technology based evapotranspiration estimation for various crops. So in this particular approach, a parameter named as crop coefficient is estimated, which is based on the observation of actual evapotranspiration as well as the potential evapotranspiration with multiplication of ET naught, which is denoted as reference evapotranspiration. Now, it's during this particular formula, a few terminologies come into the picture, like what is the crop coefficient and what is the reference evapotranspiration. So, very first, we have to discuss what is the reference evapotranspiration. There are, if I go to the detail, or you can say all the development related to the potential transpiration or reference evapotranspiration, and the story started from the empirical equations. So very first various, like if I'm saying in 1930s and 40s, started from, if I'm saying the empirical equation by the Thornwett method, which is completely based on the temperature data sets. So various researchers like Thornwett, Ballan Clady, Jensen has, modified Jensen has, Turk method, Penman, modified Penman, and Penman-Montier. Number of equations are developed in the particular time series with incorporation of various weather or meteorological parameters. But among all the equations, if I'm saying the best or the most accurate method which is approved by FAO, and it is mentioned the irrigation and drainage paper number 56, which is approved by FAO, the method name is FAO Penman-Montieth equation. And the FAO Penman-Montieth equation unambiguously determine the ET0 value for various reason or the climate. And why I can say that the equation or the method is most appropriate, because it's give the most accurate results or most of the location, because it incorporate all the meteorological observations, the best determined meteorological observation as well as the location based information. Along with this, if any parameter is missing, the parameter is subsequently measured by the physics based equation. So the entire equation we can say is a physically based equation, or it explicitly incorporate all the physiological as well as the aerodynamic parameters. Although the equations are mentioned here, but what are the components within this particular equation? It is enlisted here, like as the formula is given here, ET0 formula. So what are the component here? We can say like started from net radiation at the crop surface, then soil heat flux, the mean air temperature at the 2-meter height, at the same height wind speed, saturated vapor pressure, actual vapor pressure, saturated vapor pressure deficit, the slope of between SVP curve as well as the psychrometric curve. Now might be the question may come in your mind, how we determine the all kind of parameter if we may not have the data sets, a number in between. Like at least we have to require the temperature, the temperature data sets, then humidity data sets, location data sets. What are the parameters we require for this computation? So the enlist are here in terms of table form. So the major data set should be, and it must be from the location, very first the altitude and latitude, then temperature, which is maximum and minimum for the daily scale data sets, and using this same along with this dew point temperature, ultimately computation of the relative humidity maximum and minimum, as well as the sunshine hour data sets, sunshine hour or maybe radiation parameter. And using the particular major data sets, we can further calculate these parameters which are enlisted here in this table, and these all parameters are ultimately used in computation of reference evapotranspiration. So come to the part of next component, which is the part of crop coefficient based approach ET estimation method. So the crop coefficient, what is the crop coefficient? Crop coefficient basically is the ratio of crop evapotranspiration with respect to reference evapotranspiration. Now how we can say that crop evapotranspiration? Crop evapotranspiration is simply measured by various instrumentation like scintillometer, like lysimeter, eddy covariance tower, Bowen ratio tower, then water balance method. So number of methods can be used for precise measurement of crop evapotranspiration. And with respect to reference evapotranspiration, if we make a ratio, we generate what is the crop coefficient for the particular crop at the particular location. So in the next, what are the effects of the four primary characteristics? Is ultimately on crop coefficient. So as it is mentioned here, the characteristics are the crop height, albedo, canopy resistance, and evaporation from the soil, which are a component of practices which may have a combined or integrated impact or effect on crop coefficient. Follow with a case study. So we did a work research a case study or pilot project for the area of Udham Singh Nagar of Uttarakhand, where we all in the location of Pantnagar Agriculture University, the Govind Vallabh Pant University of Agriculture and Technology, Pantnagar, we have a ET station which has the integral, which has the various sensors, name is large well scintillometer as well the micrometeorological tower. So these ground observations give us a measured observations of measured data parameters of not only the weather parameters as well as the energy flux component, energy flux parameters. So in this study, we use Sentinel-2 derived NDVI data sets, which are at the 5-day interval data sets for the period of March 2022 to April 2023 for specifically sugarcane crop, and we derive the crop coefficient. Now, how we can say that we can derive the crop coefficient for the particular area? So very first, when we use remote sensing, we have to parameterize the crop coefficient with respect to remote sensing data sets. So for the particular area specific, as we have 5-day temporal resolution based Sentinel-2 NDVI data sets, so we make a correlation with respect to NDVI versus KC value. And here we use the KC value with respect to the observed data sets from the particular tower site. So when we find out a significant correlation between KC versus NDVI, and right side the curve define the time integration based NDVI variability or KC variability in the entire period, study period. Okay, so this is ultimately give us the value of crop coefficient at 5-day interval for the entire period of the study area. Along with this, here we use the inset satellite derived PET, the potential evapotranspiration data sets, where we simply use as the component of ET naught, KC multiply of ET naught. So we make also a correlation like with observed potential evapotranspiration data sets as well as our Indian satellite data sets, specifically INSET 3D geostationary satellite derived potential evapotranspiration data sets, and when we find a quality agreement between observed versus satellite derived data sets. So this ultimately satellite pixel based data sets we are used here in final integration of crop water requirement using crop coefficient approach. So here, as I show in this slide, the results are from various crop phenological stages of the sugarcane crop, specifically the establishment phase, tillering phase, grain growth, and maturity. So if you have idea about the crop phenological stages of the sugarcane crop, it's very in terms of if I'm saying the day basis. So the establishment phase 0 to 40 days, then 40 to 135 days, then 135 to 300 days, 300 to 365 days. So this is complete a annual cycle, because as you already have idea, sugarcane is a perennial crop and it has a lifespan of around 12 months and so. So this is the overall variability of the crop water requirement and evapotranspiration using when we use a crop coefficient approach, and the totality of the particular season, particular phenological stages wise we compute here and show here the evapotranspiration rate or values which vary from 115 to 1098 for entire period. And while we compute the actual evapotranspiration for the sugarcane crop, that ultimately maximum it's vary from 1423 to 2693 for the particular. With follow of crop coefficient approach, there is another approach which is most widely used with contemporary of crop coefficient method, which is also known as remote sensing energy balance model. So what is the surface energy balance? Surface energy balance basically a total integration of energies from in form of net radiation flux and which ultimately fragmented in terms of sensible heat flux, latent heat flux, and soil heat flux. So what are the different components? If I'm saying the net radiation, so net radiation is the total of incoming minus outgoing radiation flux which is available on the ground, and which is only through the, because sun is the prime source of energy, so our solar radiation is the main integral part of the computation of net radiation flux. Then come to the sensible heat flux, the H. The sensible heat flux is the loss of heat rate, basically the flux part, through the process of conduction and convection, while the LE is the loss of heat or flux from the canopy as well as the soil surface, while the G define the heat loss or the heat accumulation in the soil or the vegetation with the process of conduction. So this is all type of like energy fluxes which make a total of net radiation. Out of all the flux component, if we have, or if we may compute the net radiation and the energy which is from the solar, sun basically, and H and G for the particular location specific using maybe instrumentation or using remote sensing based equation, or empirical, or sorry, semi empirical to physics based equation, then we easily, on the basis of residual approach, we can compute the latent heat of energy which is denoted by LE. So in the same, number of models are there, like they classified in terms of one source model and two source model. So how we can determine what is the one source model and what is two source model? Although I only enlisted here the number of like start are from one source model to follow with two source energy balance model. So what are the difference between one source energy balance and two source energy balance model? One source energy balance model combinedly define or compute the evapotranspiration, while the two source energy balance model separately estimate or compute the evaporation and transpiration. So that is a major difference between one source and two source, as well as the all among different surface energy balance model. They are also classified on the basis of what kind of approach we are using. Like there's two type of approach. One approach is the scatter plot basis approach, and second is the anchor pixel approach. If we use scatter plot, it means the scatter plotting of the data sets of two different data sets in one y-axis and one another one in the x-axis. So among this particular variability in terms of, you can say, two-dimension scatter plot between LST versus lens surface temperature versus albedo, or lens surface temperature versus PV, the fraction of vegetation basically. So that's method defined as a scatter plot based method. While the anchor pixel method, where we have to determine this very precisely what is the hot pixel and what is the cold pixel. Basically the hot and cold pixel is from only agricultural landscape. So based on the hot and cold pixel, it means the hot pixel which has the lowest or minimal evapotranspiration, while the cold pixel has highest rate of evapotranspiration because of its low in terms of LST part. So basically that difference between in terms of temperature scale basis, the land surface temperature base scale define the precise estimation of anchor pixel, and which ultimately used to define hot and cold pixel, and based on physics based equation we can further compute the instantaneous evapotranspiration. How we compute that we will discuss in later on one by one next on slides. So with a case study of scatter plot based method, the model name is SAB, and which are also widely used and also well accepted because of its advantage over other methods. So what are the SAB method? SAB method is a simplified surface energy balance index model, and it has the two major advantages. What are the two major advantages? One is it has not required any additional meteorological data sets. Like you may not required for computation of using SAB model in terms of ET part, like what is the temperature, what is the humidity, what is the net radiation. You require a bare minimum like data sets like air temperature, and it is sufficient for the particular computational part. Then further, this model concern about the extreme temperature of wet and dry condition. So that based on the wet and dry condition, we can define what is the dry edge and what is the wet edge in the entire 2D scatter plot of the data sets. So based on that, we can define the wet and dry condition among various land use and classes among all. That model was developed by the Roring in 2000. Using this particular model, We also did one study in the area of NCR along with this Western Uttar Pradesh, where we use Landsat 8 dataset which has visible near infrared band as well as the thermal band. So because whenever you use the surface energy balance model, we have to require visible VNIR as well as the thermal bands. So this is the overall methodology for SAB model to compute crop evapotranspiration, which is specifically method named as SAB, and the theory of evaporative fraction. So in this particular model, we first compute NDVI and further LST, and a scatter plot between LST, land surface temperature, versus albedo, and the albedo is derived from surface reflectance of VNIR bands. So as we plotted the scatter plot between land surface temperature and albedo, we define the wet edge and dry edge, and based on the wet edge and dry edge, we ultimately compute what is the evaporative fraction. So as we compute the evaporative fraction, we ultimately use through the net radiation as well as the soil heat flux data sets, and finally we compute what is the latent heat or further crop evapotranspiration. So how we can use this kind of method? So very first we have to plot a 2D scatter plot with in between surface temperature versus surface reflectance, or the name as albedo. So the right side of figure, a clear cut define the overall scatter plot between a LST versus albedo, while the trend line, there's two trend line, one is the radiation control line and another is the evaporation control line. What is the difference between radiation and evaporation control line? If I'm saying the radiation control line, that is on, you can say, the all the points which are lying higher side in terms of LST scale. It means this is the line, this is the trend line about all the pixel which has higher LST in terms of variability of albedo, while the evaporation control line has lower in terms of LST with variability in terms of albedo value. So as we compute the radiation control line and evaporation control line with a fragmentation of our albedo value, like for example in this figure, how we compute the radiation control and evaporation control line, we have to make a bin size, a small bin size of albedo value. Like albedo is vary from 0 to 1, so we make a fraction of maybe 5% or maybe the 1%, and based on particular bin size of 1%, 2% or 5%, what is the maximum and minimum value in terms of LST. So as we get maximum, as we get minimum, using the maximum points, LST points, we may generate the trend line of the radiation control line, and by use of LST minimum, we can generate the evaporative control line. So using this particular formula, which is mentioned here, like of evaporative fraction, the delta Th minus T naught divided by Th minus T lambda I, which is a basically formula of evapotranspiration, which is ultimately proxy of evapotranspiration. And while Th and T lambda I is defined the LST of dry pixel and wet pixel, or as I already defined, this is the trend line, a linear regression equation of radiation control line or evaporation control line, which is mentioned here in this slide. Like Th and T lambda is a simple linear regression equation, which is y is equal to mx plus minus c, and same we incorporate in the formula of the delta. So as we incorporate the formula of Th and T lambda I, we can easily compute what is the evaporative fraction for the particular area. And Rn and G we may also compute using the data sets or as well as the satellite informations, like in terms of data sets of albedo, NDVI, emissivity, or using that we can compute lambda I. And as we compute the lambda I, which is the latent heat of energy, we further transform in terms of instantaneous evapotranspiration. As you might have idea, remote sensing, whenever it's capture the image, it's a instantaneous business. So it's capture the image at the particular time, at particular fraction of second. So at that, when it's captured the image, it's defined the particular instantaneous condition of the land surface. So now the things we have to convert this instantaneous information or a time bound values, or maybe how we can convert, we can convert the instantaneous value at the instantaneous scale to daily scale. So for that we have to require daily basis then radiation data sets, and with a comparison of instantaneous data sets we can generate what is our daily scale evapotranspiration. So in this particular study we use second UTR method for the daily basis integration along with this SAB method. We validate this study with the ground observation also, as I already briefed you, this study we did for the Delhi as well as the Western Uttar Pradesh region, and we very precisely define the evapotranspiration rate and its pattern for the sugarcane wheat cropping pattern as well as the rice wheat cropping pattern for the period of 2014-15. And this work we also published in peer reviewed journal. And that study, because it's well accepted methodology part and algorithms, we validate this result with respect to a ground observation using large aperture scintillometer, which is a very precise or peculiar instrument which give you a measured energy fluxes data sets, evapotranspiration data set at the footprint scale. And here you can easily see in the left upper side of curve define a scatter plot between estimated evaporative fraction versus measured evaporative fraction, the delta value, and we find out a very quality agreement of index and model efficiency. And also in this study, as we are using the Landsat A data set which has the 30-meter spatial resolution, so we also find out which kernel window is the best appropriate to validate or comparison with respect to satellite derived with respect to observed data sets. So as we find out 3 by 3 window, 5 by 5 kernel window, 10 by 10, 15 by 15, up to 50 by 50. So out of that, 10 by 10 window is best appropriate for computation in terms of using large intermediate data sets with comparison of SFB model derived evapotranspiration data. So this is the overall structure or setup of ET station of large aperture scintillometer which we use at the time of study. Currently we augment the entire setup in Pantnagar University Agriculture Farm under our MOU or collaborative research work part. This is the overall glimpse of the sugarcane crop phenological stages as I capture last 1.5 year different crop growing stages using this large scintillometer. And basically the large scintillometer working on the principle of it's measure the structure parameter of refractive index, and as it's measure the structure parameter of refractive index, it's ultimately convert the values of the CNS square value, the same structure parameter, in sensible heat flux. So from the same tower side, we have the micromet tower which give you the net radiation value, soil heat flux value, to high temperature humidity value, as well as the sensible heat flux value. So based on the residual approach, like as we have H measure data sets, RN measure data sets, G measure data sets, we can compute LE or ET for the particular area specific, the footprint scale. So this observation ultimately used for the validation part. So earlier, as we established the same setup in the farm of ICR Indian Agricultural Research Institute at the path length of 990 meter. And currently, as we already augmented the farm of Pantnagar, where the path length is around 1020 meter. So what are the various pattern as it show in the same figure? Like what is the pattern of net radiation, soil heat flux, sensible heat flux, and latent heat flux at diurnal pattern of monthly scale. As the values are vary on x-axis from 1 to 12, which is data set started from June to next May. So you can easily find out the RN variation, G variation, H variation, and LE variation. Specifically in LE part, you can see in the last bottom right side of curve that there is a complete or very precisely defined a cropping pattern of where we use or where we measure the ET scale or latent heat of energy for 2 different crops. And that particular area or particular IRE farm has predominant with maize wheat cropping pattern. So that is the peak related to maize crop, and second peak related to wheat crop latent heat of energy scale. So like this, we can budget all the energy flux component, and in this same, we integrate the information of meteorological parameter as well as the large scintillometer based data sets after its spectral filtering and gap filling and quality assessment in aviation software, and ultimately compute what is the latent heat of energy using residual approach and further evapotranspiration. And these all precisely measured data sets of evapotranspiration we use in validation of various model where we use remote sensing and GIS, like maybe the crop coefficient approach or maybe the energy balance approach. So in the same series, now the next model is the metric, which is one of kind of most advanced one source type of model. And the metric full form, as it's mentioned here, mapping evapotranspiration at high resolution using internalized calibration method. And in this model, basically it is a upgraded version, or you can say a improved version of the civil model. Earlier, Professor Banstincian in 1995, they developed a model named as civil, which is surface energy balance algorithm for the land, and which is completely physics based model, where they determine the hot pixel and cold pixel, basically known as anchor pixel, and with internalized calibration to finalize what is the hot and cold pixel basis, they ultimately define what is the H and LE component. How they define H and component? Basically, they use energy balance approach over transmission, which is also known as the residual energy balance approach. And here, the metric model is more precisely use the high resolution data sets. Although we can or various researchers use the same metric model with the MODIS data sets also, which has the thermal band at the spatial resolution of the 1000 meter. But if you have a high resolution data sets, for example, Landsat 8 or 9, along with this, people nowadays people are using, or researcher or various scholars are used, and various parts of the globe they are using UAV data sets, unmanned aerial vehicle drone data sets also for ET estimation using the thermal band data sets. So along with this, a clear sky satellite data sets, the crop inventory maps, weather data sets, and very precise observed hourly as well as the daily reference ET data sets required in metric model for ET. So what are the various energy flux component? As very first, the net radiation, the formula as it is given here, which is basically integration of all component of incoming and outgoing short wave and long wave radiation, while the soil heat flux is comprises a derived result from NDVI, albedo, and land surface temperature. While the sensible heat flux, as I already discussed about its definition, basically the formula is defined as rho Cp dt by RH, while the rho is air density, Cp is the specific heat of the given pressure, which is a constant, while the dt and RH is a variables. Dt basically air temperature difference between two heights of 0.1 meter to 2 meter. It means here the temperature variation in terms of influx or outflux we have to define, or the temperature gradient in terms of various scale in terms of diurnal pattern, day and night time, we have to determine, so that we can precisely compute the dt, as well as the RH define the aerodynamic resistance of the heat transfer. So these two undefined, or you can say variable component, how we determine? So for that particular things, very first we have to precisely determine what is the cold and hot pixel. So as we define cold as hot pixel, there is a certain hypothesis or the methodology part or the procedure which we have to follow. Various researcher already did this study since last 15 to 20 years, and they developed various algorithm or procedure to determine. Out of that, one selected methodology just for sake of understanding in terms of quality understanding of various steps or procedure part I mentioned in this particular slide. Like in the cold and hot pixel, basically the anchor pixel, we have to determine based on the NDVI as well as the LST data sets. So as the NDVI, you can say top of the NDVI and bottom of the NDVI. Top and bottom, it means highest NDVI. The top 5% of NDVI is used for cold pixel, and bottom 10% of NDVI used for the hot pixel. Along with this, a minimum variability or minimal variability in terms of land surface temperature with respect to plus minus 0.2 degree Kelvin. Along with this, the albedo value that should be within the limit of plus minus 0.2 unit scale. So if the conditions are fixed or condition are follow up with respect to certain homogeneous patch or homogeneous pixels, so along with this, in that we choose one pixel, only one pixel for as anchor pixel of cold as well as the hot. So these hot and cold pixel ultimately make a scatter plot between land surface temperature and dt variability, which is based on some meteorological parameters named as the friction velocity, or maybe you can say zero plane displacement. So if you just go through the part of little detail of the civil manual and metric manual, you may get all the details, but sake of understanding, just based on the temperature gradient, first we finalize all the values from our observatories, and once we finalize or fix the observatories scale of this U star and RH value, then we replicate the same information with the stability parameters at remote sensing based data sets. So which ultimately based on through this internalized calibration method, as it is mentioned here, like how we can define the or internalized calibration method. In internalized calibration method, here we have to define the wind speed at the measured site might be at the 2 meter, 1 meter, or maybe the 10 feet of height, or 3 point something 3.3 meters somehow of and height, and that same values we have to further reciprocate or further compute in terms of iteration manner of wind speed at the 200 meter, and further we define what is the frictional velocity, so that we can define what is the wind flow for the particular area specific, and ultimately we have to fix, or you can say stabilize, the values of U star and RH, and which we further incorporate in the hot pixel and cold pixel determination. So based on that, we generate this particular scatter plot of dt versus Ts, land surface temperature, and compute the H here. So using this approach, we follow up in the same area of Pantnagar region using the data sets of Landsat 9, a recent, it was launched in September 2021. And after its launching, we use very first we use that particular data sets in 30th of November 2021, and we generate these results, and we also make a comparative assessment with respect to ET station, which is based on the large plus intermediate data sets, and we find out a quality agreement between observed versus model derived data sets. So once as we define the EVO transmission using crop coefficient or maybe the remote sensing energy balance model based ET, which is instantaneous ET. So we have to convert this instantaneous ET to a fractional ET, so that on the particular using this particular fraction, we can compute a 24-hour day scale EVO transmission. As it is mentioned in this particular slide, all the formulas. So we have to first we compute the reference EVO transmission using hourly data sets, and the same hourly based data sets we can further make a cumulative of 24 hours of reference EVO transmission data set. So once we derive the EVO, as we derive ET instantaneous data sets and the fractional of ET using hourly data sets, we can ultimately use in the formula of EVO transmission at 24 hours, and we can determine what is the 24-hour values of EVO transmission. And as we get the daily basis data sets, we further integrate the data sets maybe through interpolation technique, as because the data sets remote sensing data sets has a defined temporal resolution, because every maybe 8-day or 16-day data sets we have. So in between, the gap filling is done through the interpolation technique. Although there is a number of interpolation techniques, so we can use linear interpolation also, we can use weighted interpolation technique also, just to define what is the values of each and every day basis EVO transmission rate. Now come to the next topic in the same series. In advancement of technique, people are using UAV, the drone, for EVO transmission estimation, and also with incorporation of remote sensing GIS. So what are the first we have to we have to know, or we should know, what is the advantage of UAV as compared to satellite derived acquisition. Although people are using recently the UAV for the precision agriculture, for specifically crop type mapping, as well as the crop EVO transmission estimation using VNIR band, the visible near infrared band, as well as the thermal band. And if I'm saying the advantage part over the satellite acquisition or various satellite censored products, so if I'm saying UAV data sets has no issue in terms of cloud, because it's always fly below the cloud and very close to the earth surface. So we can easily get data sets, as well as the quality data sets we can acquire at any point of hours and time, where the weather is within operating limits. If there is a little bit, you can say, calm conditions are there, so we can easily fly our UAV, maybe the fixed wing or hexacopter, octacopter, any kind of UAV we have, and we can get the image for the particular area. As well as we can easily make it more mobile for any farthest point over the farm or the field, and you can say without going the particular physically going at the particular corner of the field. As well as we can compare the several satellite data sets in terms of its adaptive for the site selection. any data sets anywhere, maybe it may be the forest ecosystem, agriculture ecosystem, water bodies, or orchard area, any kind of, with respect to site selection, we can easily get the image as the time we required. Like if we require daily basis data sets, if we require weekly data sets, if we require 3 days data sets, we can easily acquire using UAV system. So we simply mounted a very light weighing sensors, which is basically have the red, green, blue cameras or multispectral camera or the thermal camera at the same time, and collect the very high resolution imagery. And that imagery always below in terms of some meter resolution in terms of spatial scale. So these high temporal and spatial scale uh, resolution images, we relatively that always low operational cost, and as well as always near real time image acquisition and same time processing, we can easily get the very quality result for mapping and monitoring of UV. So although there are number of type of UAV are there in the market, like as I mentioned from a research paper, review paper, I put that particular figure. There are number of type of UAV, unmanned aerial vehicles or drones are in the market, like Quest UAV, 200 UAV, then MK Octa XL US 12, then DJI S1000, the EB classic, then Hover. Number of type of UAVs are there currently in the market, which can be used for various purpose of agricultural application. So with follow up of one case study, I put in my slide, like how remote sensing energy balance method can be used with the data sets of UAV for ET estimation. So here, as the simplified surface energy balance model, which is basically uh, compute the fractional of UV transmission using the data sets of the temperature, basically the thermal sensor data sets, and the information as it is incorporated the surface temperature as well as the canopy temperature. So these can you can say the hot temperature and cold temperature for the particular any kind of canopy, it's ultimately define the psychrometric constant, and these all value the scaling factor, the fraction of your transmission and reference your transmission incorporate and further ultimately compute the actual input transmission, which is very much give the quality and very in very few, you can say limited time, it's give you the results. You can say whenever you required a very limit, and you can involve, you can integrate and the results and precisely define what is the transmission rate. So as they capture the image for basically a plantation of pecans in the area of the Mexico, the study was done by the Mocari in 2022, published in a peer-reviewed journal, and where they choose the thermal imagery of the particular area and make a comparison of the applied water-based evotransmission as well as the modified SAB operation model-based evotransmission rate, and they find out very precise correlation among actual evotransmission as well as the remote sensing based evotransmission. Where you can say that remote sensing means basically UAV thermal imaging based evapotranspiration results give you very precise observation about what is the rate of evapotranspiration, and accordingly you can apply the water at the farm. Then in the next topic as water stress assessment using remote sensing and GIS. Although water stress cause a significant and quality reduction in terms of final growth and development of the crop, and because it's ultimately reduce the photosynthesis rate and impact on growth and development of the crops. Although various or numerous researchers demonstrate various utility of ground observations along with this, basically in terms of canopy temperature. So they use the utility of the canopy temperature in water stress reduction and quantification. So in this method, they basically make a difference between TC minus TA, or you can say the canopy temperature versus air temperature difference. So as the canopy temperature is increased as compared to air temperature, it means this is a condition of the stress. While if TC minus TA is less, it means the air temperature or it's close to zero, you can say in negative, it means air temperature is always higher as compared to the canopy temperature, which is a normal condition for the crop growth and its development. Although various methods are used by various researchers, like field scale crop water stress can be detected using with difference of canopy temperature and air temperature, as well as the stress degree day, like SDD formula or SDD methods. But while in using remote sensing and GIS, They are specifically use the spectral information of visible near infrared band. Might be they here they use the near infrared as well as the short wave infrared band information, as well as the thermal data sets. Like in previous study, as I show you, the UA based, where they use the TC minus TA, basically time of temperature or air temperature difference for the particular area specific, and determine what is the crop ET and the water stress in the particular area. So in follow up that of water stress assessment using remote sensing GIS, I put one case study for assessment of one kind of index which is most widely used by various researchers to determine the water stress, and the name of this particular index is VWSI, Vegetation Water Stress Index, and which is basically a 2D scatter plot between near infrared band and short wave infrared band. And as it is mentioned here, that left side of the particular figure in the slide define that scatter plot of NIR reflectance versus short wave infrared band reflectance, where the points of A, B, and C and D. So what are the A, B, C, and D? As it is mentioned in the text also, like A define a full canopy with canopy cover with saturated condition. It means there is full water or well water condition. While B define a full canopy cover with unsaturated condition. It means this, although the canopy is there, but there is a water stress condition, or maybe you can say water unavailability condition or dryness of condition. While C define the bare soil but with saturated condition. It means a fallow field, or maybe the plowed field, or maybe the bare field with full of moisture condition. While D define the bare field with unsaturated or dryness condition. While E and F define the partial canopy coverage in saturated or partial canopy coverage of the unsaturated condition respectively. So as we define this particular, you can say points, basically how we can define this particular points, as I already discussed in S7 model, we simply define based on the a small or minute bin size of all our x-axis or y-axis. So based on that, we can define what is the precise value in terms of the particular edge line in the both scatter plot. So with using this particular scatter plot information, which is a normal, you can say a linear regression line of AC and BD, and here this information we ultimately use the linear regression equation in computation of vegetation water stress index. So as author the Dungwal et al. In 2016, they published their work for the area of Haryana and the parts of Western Uttar Pradesh, specifically the Meerut region. And so they use the data sets of the data sets of remote sensing based sensors and compute the spatial temporal variability in the crop water stress scale based on VWSI, vegetation water stress index value, based on at the same scatter plot, and the same information as the integrated derived for the particular season of 2009 and 10 and showed in this particular slide from November to April. And the VWSI value is vary from 0 to 1. And how we can say its value is on the stress condition or normal condition. So as high of VWSI, vegetation water stress index value, it shows the effect of the crop water stress. So if you find out the results, a comparative, you can say temporal trend of from November to April of VWSI, you can find out in November the VWSI value is on higher side around 0.5 and 0.4. There's two line of scatter plot, or you can say the trend line, which is for representing for the area of Haryana and Uttar Pradesh. But as you can say over the time the crop growth takes place, because that area is well irrigated in terms of maybe surface or maybe the subsurface, the groundwater conditions, full of conditions. So with this increment in terms of crop growth and its development stages, the VWSI values decreases and minimum in the month of March, which represent the peak vegetative stage at the time. And after that, as the senescence started, the VWSI value again increasing with respect to the senescence as well as the crop stress condition of the particular period. Now in the same we follow up the next topic, touch upon our last and final topic, which is the irrigation water requirement using remote sensing and GIS. And very first, what is the irrigation water requirement? So basically, in the irrigation water requirement is the difference between crop water requirement and effective precipitation. As we already discussed in previous slide, what is the crop water requirement, but effective precipitations are defined based on how much water qualitatively used by the plant for its growth and development. So IWR, as the formula is mentioned, IWR is equal to crop water requirement minus effective precipitation. So the effective precipitation or effective rainfall is determined as it is mentioned in the slide at the FAO formula, which is well accepted based on the precipitation data sets. If the rate of precipitation higher than 75 and lower than 75 at the per month scale, so based on that we can easily compute the effective rainfall, effective precipitation. And what is the effective precipitation? The amount, the fraction of water which is percolate below the root zone and the particular part of water which flow away from the soil surface as runoff. So if we remove that particular part, the remaining part, which is the water content, which is stored in the root zone and can be used for the plant, it's in growth and development. The remaining part is so-called effective rainfall or effective precipitation. So in the same area of the Udham Singh Nagar, as we did the study and we compare the crop water requirement with respect to irrigation water requirement, as you find out the values of the monthly scale in the left side of the figure, the values of the up from July, August and the parts of September are completely blank. Why it is so? Because here as all irrigation water requirement it as 0 because of the availability of the monsoon in this particular period. Because here as we also use the inset derived or inset observed rainfall data sets with integration and computation of irrigation water requirement and with integration of crop water requirement, as I earlier discussed in my previous slide, with integration of the effective precipitation using the effective precipitation formula, and we finally compute the seasonal irrigation water requirement for the particular area at the entire study period. And in this particular period of 22-23 growing season, as we find out the total irrigation water requirement for the sugarcane crop vary from 1000 to 2046 mm for the period. Now come to the part of various global and regional products. Very first, our Indian product and the web portal. The website name is MOSDEC, which is Meteorological and Oceanographic Data Archival Center, where you can get the hourly as well as the daily scale basis various meteorological or weather parameter which is observed by our Indian satellites. Earlier it was captured by the Kalpana 1. Currently it is captured by the INSAT 3D and INSAT 3DR. At every half hour, 30 minutes interval data sets we can capture from the geostationary platform, and the data sets are available. You just make a only login on the particular web page or web portal and you will get the data, all the data set free of cost for the pan India level at different spatial resolution, might be from 1 kilometer to 8 kilometer. The second is the MODIS, the moderate resolution imaging spectroradiometer, where you will get the net UV transmission at 8-day composite values or 8-day values or yearly basis of daily values. And within this particular products, you may get the value of the potential UV transmission, total UV transmission value at the 8-day composite as well as the yearly basis for global scale. And the URL, or you can say the link, is there in this particular slide, where from where you can simply generate your login credentials and you may get the data sets free of cost. In the same series, one of kind of product is monthly actual UV transmission, which is based on spatial resolution of 1 kilometer resolution data sets, as well as they are method of SAB operational, the simplified surface energy balance operational method type of surface energy balance method, and from where you will get the data sets of actual UV transmission at the global scale on monthly scale data sets. One of kind of GLAM data sets are there. The data sets and that particular data sets has a qualitative information in terms of, because it's give data sets transpiration, evaporation and the interception separately, and you can directly download the particular data sets from the particular websites as it is mentioned there in this particular slide. Now in the same, a very high spatial resolution along the temporal resolution data sets, if I'm saying the EE-flux data sets, which is a derived product from Landsat 8 and Landsat 9 data sets at the global scale, as well as the method as they use is metric model, so which is one source energy balance model, completely physics based model, and their ET products are readily available for global scale. So every 16-day composite of Landsat 8 and 16-day composite of Landsat 9, the data sets are available at the actual crop yield transpiration as well as reference yield transpiration for global scale. So these all kind of data sets you can easily download for a regional scale to global scale for various kind of studies, and these all data sets are freely available at any point of time and scale basis. So this is all about the particular lecture, the topic of crop water use, crop water requirement, water stress, irrigation water requirement using geospatial technology. Thank you from my side.